I hope you all are doing well today. We are going to be talking about the transient analysis of first order circuits today, and specifically, we're going to be talking about what's called the natural response. So I'm going to write some of this stuff down. So transient analysis of first order circuits and natural response. So the title of this lecture actually has quite a lot to unpack here. So the first thing that I want to talk about is what a first order circuit is. Okay. So first order circuits are characterized by first order differential equations. So what we're going to see shortly when we look at our generic circuits is that when we apply Kirchhoff's current law in one case and Kirchhoff's voltage law in another case, we are going to get a characteristic equation that tells us how this generic circuit behaves, and it is going to be a first order differential equation. I fully understand that the overwhelming majority of you guys have not yet had Math 245, so this is very likely your first introduction to differential equations. We are going to approach things from um, a intuitive method. So having no background in differential equations is not going to provide any sort of hindrance for us today. Another way that we can think about a first order circuit is that the circuit contains only one equivalent energy storage element. So that means that if it has multiple inductors, we'll be able to um, simplify them down to a single inductor. Similarly, if there were multiple capacitors, we could simplify those capacitances down into a single capacitor. We won't be dealing with any circuits that contain both inductors and capacitors. That would be a second order circuit. Nor will we be dealing with any circuits where we can't combine our energy storage elements into a single equivalent energy storage element, because that would wind up being a second order or higher system. So realistically, all we're going to be dealing with for today, Friday, and Monday's lectures are circuits that contain resistances and inductances, or circuits that contain resistances and capacitances. Okay. So that's what a first order circuit is. So transient analysis just means that we are going to be analyzing the circuit when it is undergoing a transient condition. And a transient condition simply means that our circuit is undergoing some amount of change. So all of the circuits that we're going to be dealing with for the next several days will have switches so that we can make some type of relatively quick or instantaneous change in the circuit. And we're going to see what shakes out from that change occurring. And then lastly, natural response simply means that these first circuits that we're going to look at are going to have any independent sources effectively taken out of the system so that we can see just what the behavior of the energy storage element and the resistor is doing. When we meet on Friday, we'll deal with the total response, which is what happens when our independent sources are left in our systems. So we're going to kick things off by looking at an RL circuit. Okay. So this is going to be a very generic RL circuit, um, something akin to this. So let's say that I have, um, let's put a current source right here. And it has some magnitude IS like so. And at this node up here, there's going to be um, a switch essentially. And this would be an example of a single pole dual throw switch. It's not important that you understand that. We'll talk our way through it here in a moment. I'm going to draw the rest of the circuit like so. And let's say over here on the right, I have some resistance, which I'm going to call Req because it's representing the equivalent resistance of some larger system, or potentially the equivalent resistance of a larger system. And also, I'm going to have some inductance over here that I'm going to call LEQ, representing the equivalent inductance of some larger system. Okay. So let's say that our switch is originally closed at position B before switching over to close at position A at t is equal to 0. So that's what this symbol is trying to mean. So my switch starts off closed at position B, meaning that my current source is connected to the network containing REQ and LEQ for all points in time before t is equal to 0. And then after t is equal to 0, my current source is then just connected to the short circuit on the left, and it is then disconnected from the network containing REQ and LEQ. So that's what's going on with our switch. Okay. So what we're going to try to do today is to figure out how some of the electrical signals in this system are going to behave. Probably the most important one here is going to be the inductor current. So I'm going to put that in red like so. So here's my inductor current, IL, as a function of time. We're going to try to sort out what it's doing for all points in time. And then a couple of other quantities that we might wind up messing around with might be the voltage drop across our inductor, which will be VL as a function of time. And I'm also going to define a voltage drop across my resistor, like so, VR as a function of time, where I've chosen to put the positive polarity terminal on bottom so that that current IL of T winds up flowing through the positive polarity terminal of that resistor during the transient condition. Okay. So this is our generic circuit of interest, and we are going to look at it at a few different points in time. Okay. So let's start by kind of figuring out what is happening for t is less than what I'm going to call 0 minus. Okay. So 0 minus is the instant right before our switch changes states. Okay. So if we assume that our switch has been closed for a very long time, we can treat this as if it is a DC circuit. Okay. So I'm just going to make a note here. Treat the circuit as if it's, let's call it at DC steady state. Okay. So that means that our inductor is actually going to look like a short circuit. Okay. So I'm going to redraw our circuit under that condition. So I've got my terminal A over here is going to be open circuited. Terminal B is going to be connected to my switch. All right, so something like this. Here's my equivalent resistance. Actually, my inductance should be drawn as a short circuit. I mentioned that a moment ago. We're drawing the inductor as a short because we are at DC steady state. This is going to be my inductor current, and I'm going to label this as IL at 0 minus. So at this particular time, which is the instant before the switch changes state, this is representative of everything that's happened before this point as well, because we have a DC circuit, so everything is constant. So I'm really only care about what's happening at the instant before the switch changes state, because we know that the current flowing through an inductor cannot change abruptly. So whatever its value is at the instant before the switch changes state, it has to have that same value at the instant after. But again, this is technically representative of everything that's gone on before our switch changed. Okay. So this is going to be my voltage, VL at 0 minus. This will be my voltage, VR at 0 minus. And for the most part right now, we're really only going to pay attention to what's going on with our inductor current. So I would greatly appreciate if one of you could analyze this circuit. You should be able to do it by inspection and tell me what the inductor current is actually doing at t is equal to 0 minus.
Does it not just equal IS?
It absolutely just equals IS. Thank you for that, William. So, since our inductor is being represented by a short, and we have some equivalent resistance Req in parallel with that short, all of our source current should flow through the short, which is really the inductor, avoiding that resistive path Req. So IL at 0 minus is equal to IS. Okay. So what does this mean for the inductor? Well, we know that the energy stored by an inductor, and actually, let me write this as capital W, since this is technically a DC quantity. So the energy stored by our inductor is going to be 1/2 LEQ times IS squared. So assuming our source current isn't 0 amps, meaning that we have an energized system, our inductor has some amount of energy stored in it, okay? So that's important because what we're looking at during the transient condition is really how our inductor is going to wind up distributing its stored energy to the remainder of the system once we take that current source away, okay? So what I'm going to do over here is I'm going to draw a little bit of a graph. Okay. And so what we're going to do is we're just going to keep track of how the current in the inductor is behaving as a function of time. So this is going to be IL of t. This is going to be t is equal to 0. And we just analyzed this circuit and we found that our inductor current was some constant value. Sorry, don't know why it lagged there. of IS up until the point t is equal to 0 minus. So we are approaching 0 from the left. Okay. What we're going to do now is we're going to fast forward in time by some large amount. Okay. So I want us to figure out what is happening for t greater than infinity. Now, I know this seems weird. So I'm using an engineering version of infinity, and we'll talk about it a little bit more in class at the beginning of class on Friday. But what I really mean by this is a long time after the switch changes state. Okay. So essentially, if we wait for long enough, our system should wind up going back to a DC steady state condition because we only have DC sources and stuff like that in our system. Okay. So if we make some sort of perturbation by changing the state of the switch, if we wait long enough, our system will settle back to DC. Okay. So we're going to analyze this circuit once again as if it's at DC steady state and kind of see what happens. Okay. So once again, we're going to treat the circuit as if it's at DC steady state. And in this case, since we're a long time after the switch has been closed at position A, our new circuit should look something akin to this. Okay. So here is our switch closed at A. B over here is now going to be open circuited. Here's our current source IS. And then over here on the right is going to be our network. Here's our REQ. Once again, our LEQ is going to look like a short circuit because we're assuming we're at DC steady state. We've waited long enough for that to happen. And here is our inductor current, IL, at t is equal to infinity, which is what we're actually interested in. But I'm going to go ahead and make a note that this would be the voltage drop across our inductor at t is equal to infinity. And this would be the voltage drop across our resistor at t is equal to infinity, just if we happened to be interested in those quantities. Okay. So I would appreciate it if one of you could tell me what the inductor current is here at t is equal to infinity by analyzing this circuit.
Is it
Isn't it
just
zero?
negative IS?
So it's not going to be IS. Whoever said it was 0, which I think was Colin, is correct, right? So if we were to apply Kirchhoff's current law, what we could see is that the current flowing in to this node right here is IS. The current flowing up is IS, which means this current flowing across this way has to be 0 amps in order for Kirchhoff's current law to be satisfied. So none of the current that is provided by our current source actually makes it to our network containing our resistor and our equivalent inductance. And from that, we can say that IL at infinity is 0 amps, and the energy stored at this point in time is going to be 0 joules. Okay. So if we go back to our graph up here, and let's say that this point in time represents our engineering infinity. Okay. So a long time after our switch has changed state, we should see that the current flowing through our inductor is 0. So I'm going to make some annotations on this graph really quickly. Okay. So everything to the left of 0 is a DC steady state condition. I'm going to put kind of a dashed line up here, and everything to the right of this dashed line, so this is after we've allowed our system to come back to a DC steady state condition, is obviously also DC steady state. And then everything here in the middle between 0 and infinity is what we're going to call our transient condition. And this is when our system is undergoing the effects of the change of the switch changing states, right? So I'm just going to make a note up here. This amount of time between 0 and infinity is our transient condition that we are really interested in for today, okay? So now let's figure out what's happening during that transient condition. So this would be for 0 plus is less than t is less than infinity, okay? So we're going to figure out what happens over that whole range of time. So our circuit is undergoing a change, which means we cannot consider that our circuit is at DC steady state, okay? So we're going to have to treat our inductor as if it's actually behaving like an inductor. So if I were to draw our circuit here, I would have something that looks very similar to what we had at t is equal to infinity, except that our inductor is actually going to be represented by inductance. So here's my switch closed at position A. My current source. Here's my open circuited terminal B for my switch. My resistance REQ. My inductance LEQ. My inductor current IL of t. So we're looking at it over that entire span of time, so I can't just boil it down to a single instant. Here's VL, and here is VR. So let me try to describe in words what is happening, and then we'll try to sort out a mathematical relationship that obeys with what's going on, okay? So we learned, I believe it was a week ago, last Wednesday, when we were discussing inductors and inductances, that the current flowing through an inductor cannot change abruptly. So that means that if the current flowing through the inductor was IS the instant before the switch changed states, then the current flowing through the inductor will be IS at the moment after the switch changed states. So another way to think about that is that the inductor had some amount of energy stored in it right before the switch changed states, and it has to have that exact same amount of energy stored in it the moment after the switch changes states. But we've changed the position of the switch and disconnected that current source. So what we're going to see is that over time, our inductor is going to gradually transfer its energy to the resistor, which is going to convert that stored electrical energy into heat until we reach DC steady state again, at which point all of our transferred energy has been converted into heat and our inductor current falls back down to zero. Okay. So that's a kind of word description of what's going on. Now let's see if we can support that with some math. Okay. So what I'm going to do is I'm going to apply Kirchhoff's voltage law around that right-hand loop. Let me just put at right-hand loop here. And so what we would see, starting from the bottom left-hand corner of our RL network, we would have VR of t plus VL of t is equal to zero. So Kirchhoff's voltage law is satisfied. The sum of the voltage drops around this closed loop is equal to zero. Nothing wild or crazy happening here. Now, as it turns out, we can express both of these voltages in terms of our inductor current, since during the transient condition, our inductor current is just going to flow around that right-hand loop. So using Ohm's law, we would have Req times our inductor current, IL of t, plus, and this is equation 1 from our inductors and inductance lecture, the voltage drop across our inductor is going to look like L, or LEQ, times the derivative of our inductor current with respect to time. So this is an example of a first order homogeneous linear differential equation. Okay. And again, fully understand that the overwhelming majority of you probably haven't been introduced to differential equations before. So I'm going to try to simplify the process for solving this as much as I can here. So what we're trying to figure out is IL of t as a function that effectively satisfies this equation. So I have my inductor current function multiplied by some constant Req plus the derivative of my inductor current function multiplied by some constant LEQ, and they need to add together to make zero. So what I'm really looking for here is a function that when I add it and its derivative, they might add together to make zero. Does anybody have any thoughts on a function that the function and its derivative are essentially the same thing?
Could it be the function of E of t?
So it'll be an exponential function, okay? So let's make an educated guess. So let's say that IL of t will be of the form A, where this is just an arbitrary scaling factor. We'll figure out what value it has in a couple of moments. E to the ST, where S is what's known as the natural frequency or the eigenvalue of the system. And it's just describing how this exponential function either decays or grows. Okay, we're going to wind up figuring out what value S has to have in order to satisfy this equation in a moment as well. Okay. So if we substitute in IL is of the form A times e to the st, what we're going to wind up getting is REQ times AE to the st plus LEQ times the derivative with respect to time of AE to the st as well. This is equal to 0. And now I'm just going to perform that derivative, okay? So if I take the derivative of A times e to the st, I will just get S times A times e to the st. So that would look like REQ A e to the st plus S LEQ A e to the st is equal to 0. And now I'm just going to rearrange things a little bit. Okay. So there's a common factor of A in both of my terms, so I'm going to pull that out. And there's a common factor of e to the st in both of my terms, so I'm going to pull that out. And what is left behind is just REQ plus S times LEQ. And then this has to be equal to 0. So this bit in the middle is what's commonly referred to as the characteristic equation for the system. Okay. So it's what's really going to tell us how this guy behaves. And I'd like to explain that here briefly. Okay. So there are a couple of different ways that this mathematical expression would be equal to 0. The most obvious way is that if A, our scaling factor, is equal to 0, then this thing is obviously equal to 0. That's what's called a trivial solution. And what it represents is the case where we didn't have any energy stored in our inductor to begin with. Or effectively, it's the case where IS is equal to 0. Okay. So that isn't true here, or at least we're assuming it's not true here, because we are working under the conclusion that we had some energy stored. Gustavo asked, why are the A and the E to the ST separated on opposite sides? That's just because it's how I prefer to write it. I could have lumped them together if I wanted to. I just don't do it. So no other reason than I don't like the look of it. So another way that this equation could be equal to 0 is if S happened to be negative, so that we had exponential decay and we waited for long enough of a time, okay? Well, that really doesn't work for us either, simply because we want this to always be equal to 0 over this interval, not just if we happen to wait long enough, okay? So really, what we're doing is we're trying to figure out what makes our characteristic equation equal to 0, which will wind up being some very specific value of S, right? So if I come over here to the right, and I say that REQ plus S times LEQ is equal to 0, then I can simply solve for S. And what I will find is that S is going to be negative REQ over LEQ. So this tells us that the rate of our exponential decay or growth is actually related to the circuit elements that we have in our system, which is good. It's nice that the system behaves a particular way because of the elements that are in the system, okay? So if we put this result in our expression for IL of t, we would now have that IL of t is equal to AE to the negative REQ over LEQ multiplied by time, okay? And this is technically only valid for 0 plus is less than t is less than infinity. Sorry. That infinity symbol looks crappy. So now our task is to figure out what is going on with A, okay? And this is a little bit easier to sort out, actually. So we know that our inductor current at t is equal to 0 minus has to be equal to what's going on at t is equal to 0 plus, okay? So we could say that IL at 0 minus must be equal to IL at 0 plus. This is the relationship that we came up with last Wednesday when we were looking at the derivative-based relationship, and notice that the current could not instantaneously change. And so now I'm literally just going to sub in values. Well, at t is equal to 0 minus, we found that IL was simply IS. Okay. At t is equal to 0 plus, we would have AE to the negative REQ over LEQ times 0. Well, e to the 0 is literally just 1, which means A is equal to IS, but more generally, we could say that A is equal to IL at t is equal to 0 minus, okay? So putting all of what we've done together here, we could now say, let me just write a note here. Putting all of this information together, IL as a function of time is going to look like a piecewise function, okay? So I'm going to say that it's going to look like IL at 0 minus for t less than 0 minus, and it's going to look like IL at 0 plus e to the minus REQ over LEQ multiplied by time for t greater than or equal to 0 plus. So I've done a couple of little things here that I'd like to explain. The first is, here I said A is equal to IL at 0 minus, and here I say that A is essentially IL at 0 plus. I'm able to make that change because my inductor current doesn't change abruptly, okay? So that doesn't hurt anything at all. Now, when we defined this function earlier, we defined it over the interval from 0 plus is less than t is less than infinity. And I've effectively thrown the infinity away when I wrote it down here. Well, that's because we have exponential decay. So we know that over time it's going to settle down to 0. So what it's doing after t is equal to infinity is the same thing that it was doing if we just let t get large enough. So I haven't lost any information by representing it in that way either, okay? So this equation right here is how our inductor current specifically is going to behave. So now, before we get into working some problems here, I want us to go back up to our graph A and kind of fill in the gap. So what we should see is that during this transient condition, our inductor current gradually decays from IS down to infinity, and the rate of decay is dependent on the value of REQ and LEQ. Okay, so are we all, okay with that?
Yes.
All right, so now I want us to think a little bit about what's going to happen with our inductor voltage and what's going to happen with our resistor voltage. Okay. So let's talk about our resistor voltage first, because it's the easiest thing to understand what's going on. So knowing what my inductor current is, what do you guys think my resistor current, excuse me, my resistor voltage is going to do? Or how can I find the resistor voltage? I'm trying to figure out a way to phrase this where you guys can catch what I'm throwing. So I'll go ahead and answer the question because I feel like I phrased it poorly and you guys aren't following me. But essentially, what's going to happen with the resistor voltage, at least during the transient condition, is we can just use Ohm's law and say that VR is just REQ times IL, right? So what we would observe is that our resistor voltage, VR of T, is going to be whatever our resistor voltage was before our switch changed states, which in this case happens to be 0. I can say that by inspection. And then after our switch changed states, it's going to look like R EQ times IL at 0 plus e to the minus REQ over LEQ times time for t greater than or equal to 0 plus. But I'm going to go ahead and take this one step further here, okay? So REQ times IL at 0 plus is literally just the voltage drop across the resistor at t is equal to 0 plus. Okay? So I could instead write this as VR at 0 minus for t less than 0 minus, and then VR at 0 plus for t, e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. Okay. So the voltage drop across our resistor has the exact same form as the current flowing through our inductor, which should make sense because the current flowing through our inductor is just the current that's flowing through our resistor. Well, if I wanted to figure out what was going on with my inductor voltage, I would have something like this. So I could say that VL of t is going to be just whatever it was doing at 0 minus, which in this case happened to also be 0 volts, because the inductor was a short circuit at t is equal to 0 minus. And then if I look back at my graph or my circuit during the transient condition, REQ and LEQ are in parallel, so the voltages across them are the same. the inductor voltage is defined as the opposite polarity of the resistor voltage. So that would just be negative VR at 0 plus e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. But negative VR at 0 plus is just VL at 0 plus. So I could put this only in terms of what's going on with the inductor voltage as VL at 0 minus, T less than 0 minus, and then VL at 0 plus, e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. So we can see that our inductor current, our resistor voltage, and our inductor voltage all have the exact same form. So what I'm going to do now is I'm just going to come up with an even more generic representation that we can use for literally any quantity in one of these systems. So what I'm going to say, I'll do this in purple, I guess, is that in general, for an RL system, our natural response, I'm going to call that Y sub n of t. So this is valid for any current or any voltage in our system, can be expressed using the following relationship. We'll have Y at 0 minus for t less than 0 minus, and then Y at 0 plus, e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. So this equation will work for literally everything. Okay. And from this equation, we can see that we just need 4 different pieces of information. Okay. We need to know, sorry, I don't know why my stylus isn't drawing. Give me just a second. Y at 0 minus, Y at 0 plus, REQ, and LEQ. If we can figure out those 4 pieces of information, we can solve for any current or voltage in an RL circuit that is undergoing a transient condition. So I would like for us to now work an actual example problem and see how all of this stuff kind of sorts out. And I'm going to show you guys the step or my preferred method for solving these circuits. Okay. So this is the circuit that I am interested in. Okay. So down here, I'm going to have a current source. And let's say that this is a 5 amp current source. And it is connected in parallel with a 2 ohm resistor, like so. Okay. Over here, I'm going to have a switch. This is going to be terminal A. Down here is going to be terminal B. and my switch is initially connected at A, and it's going to flip down and connect at B at T is equal to 0. Down here, I have a 7 ohm resistor. Across here, I have a 10 ohm resistor. In parallel with this 10 ohm resistor, I have a 100 millihenry inductance. And then lastly, over here, I have a 3 ohm resistor. So this is our circuit. It seems a bit more complicated than our generic circuit, but we'll get through it. I'm interested in finding our inductor current. So let's call this current right here IL of t. And then I'll let you guys pick either a resistor current or a resistor voltage, and you just tell me like which resistor and then the current or voltage. So somebody spit something out.
7 in voltage.
So the voltage drop across the 7 ohm resistor. So let's call that VR of t, like so. Okay. So this is the circuit that we're going to analyze, and these are the two quantities that we are interested in. Okay. So our first step when we approach any transient analysis problem where we have an RL circuit is going to be to analyze the circuit at t is equal to 0 minus. So this is us figuring out what's going on before our switch changes states, and it is essentially what's giving us our initial condition for how the inductor specifically is behaving. Okay. So I'm just going to make another note here. This one is incredibly important. DC steady state. So anytime we're looking at the circuit at t is equal to 0 minus, we are dealing with a DC circuit. Okay. So at this particular point in time, my circuit looks something like this. So here's my 5 amp source. Here's my 2 ohm resistor. Here's my terminal B, which is open circuited. Here's my 7 ohm resistor. Here's A. Since my switch is connected here, I'm just going to draw this as a short circuit like so. Here's my 10 ohm resistor. Here's my inductor. Because we're at DC steady state, the inductor looks like a short circuit. Here's my 3 ohm resistor. I'm interested in finding this current, IL, at 0 minus, and I'm interested in finding this voltage, VR, at 0 minus. So, can anybody tell me how we might find either of those two quantities? So let's start with the easier one. So Trevor, you suggested that IL is going to be equal to 5 ohms, or excuse me, 5 amps. I disagree with that, but let's start with the voltage drop across the resistor because I feel like it's easier. Okay. So how much current is flowing through the 7 ohm resistor?
0.
0. So if no current is flowing through the 7 ohm resistor because it's open circuited on one side, what's the voltage drop across the 7 ohm resistor?
0.
There we go. So hopefully that wasn't too difficult. VR at 0 minus has to be 0 volts. Okay. Now, Trevor, I'm going to explain to you why the current flowing through the inductor isn't just 5 amps, right? So essentially, I've got 5 amps that's coming along up to this point right here. And then it sees this path, which contains 2 ohms of resistance, and then it sees this path, which contains 3 ohms of resistance. Then that split current is going to flow down and recombine at that bottom node. So it doesn't see just the short by itself so that all of it will flow through the 3 ohm resistor. It sees essentially 2 ohms in parallel with 3 ohms. So how might we go about finding that current?
Current
Since
division.
I'm sorry, what was that?
Current division.
Current division, sure. Um, so it should be really easy. Like I think intuitively it's going to be 3 amps, but let's do it more formally here. We could say that VL of 0 minus is going to be 5 amps times, so I would have 1 over 3 ohms right here. Actually, it'll be 2 amps, sorry. 1 over 3 ohms divided by 1 over 2 ohms plus 1 over 3 ohms. And I'm going to throw that in my calculator just to make sure my mental math is working correctly. Yep, 2 amps.
Should the 0 minus be IL?
Oh, yes, sorry about that. That should totally be IL, not VL. Thank you for that. I just mislabeled it. Okay. So before we move on to our next step, does anybody have any questions, comments, or concerns about the analysis that we performed here?
I have one question. Will we ever be doing conductance or no?
So conductance meaning the inverse of resistance? No. We will only deal with resistors and inductances or resistors and capacitances.
That's what I meant, capacitance.
Yes, so we will definitely be dealing with capacitances, and as soon as we finish this particular example problem, I'll introduce how we're going to deal with capacitors. Um, it's going to be extraordinarily similar. I'm going to go through the derivation, but I will do it much faster because it is almost identical, and then we'll work one example problem, and that'll be the end of class essentially. All right, so let's move along to step number 2. So what we're going to do here in step number 2 is we're going to analyze the circuit at t is equal to 0 plus. Okay. So this is the specific instant in time after the switch has changed states. So we're not looking at things over a range of times like we did when we were deriving things. We just want to know what's happening in that one particular moment. Okay. So I'm going to draw our circuit. So here's the 5 amp source. Here is our 2 ohm resistor. Now, terminal A is going to be open circuited. So that's this guy right here. And then B is going to be closed to our switch. So here's B. There's that 7 ohm resistor. Here's our 10 ohm resistor. Up here is where our inductor is going to be. We'll talk about that in just a moment. And then here is our 3 ohm resistor. So let's talk about what's going on with the inductor right now, okay? So at t is equal to 0 plus, the current that is being carried by the inductor is fixed, right? So I'm going to make a note of that over here on the right. So IL at 0 plus must be equal to IL at 0 minus, which was 2 amps. The inductor current can literally not be anything other than 2 amps without us violating the laws of physics, essentially, okay? So the current flowing through the inductor is fixed. The voltage drop across the inductor can be whatever the hell it needs to be, right? There is no constraint on the voltage drop across an inductor changing abruptly. So how I'm going to choose to represent the inductor at this very specific instant in time is as an independent current source, because the current flowing through it is fixed, but the voltage drop across it is whatever it needs to be, which is exactly how we would describe the behavior of an independent current source. So I'm going to replace my inductor with a current source where the current direction is going to be the same direction as IL was defined, which is flowing left to right through the inductor. And it's going to have the same value as the inductor current had at t is equal to 0 minus, which happens to be 2 amps. We don't need to do any work whatsoever to find IL at 0 plus, because we already did that work when we were analyzing the circuit at t is equal to 0 minus. So the only unknown quantity that we're dealing with now is just the voltage drop across our resistor at 0 plus. So before we get into this analysis, is everybody clear on why I have replaced our inductor with a current source? I see a couple of people giving a thumbs up. For what it's worth, if you wanted to just draw it as an inductor and then make an annotation that says the current flowing through it is 2 amps or whatever, that's perfectly fine. I prefer to look at it as if it was a current source, because we're just going to use DC circuit analysis techniques here. So I'm just trying to make it look as quote unquote normal as possible. Okay. Okay. So does anyone have any thoughts on how we might find that voltage?
Could you do a source transformation of the 2 amp and 10 ohm resistor?
We technically could. It wouldn't necessarily be a bad idea here. So if we did a source transformation, then we could do voltage division. So there's nothing wrong with your instincts here. There's just a much easier way to do it. And the only reason it's easier is because of the values of the resistors that were chosen. Okay. So let me explain what I mean. So directly in parallel with the 2 amp source, we have a 10 ohm resistor. In fact, I'm going to identify my nodes here really quickly. Maybe it'll jump out at you if I help out with that. So here's one node. And then here's a second node. And then here's a third node. And obviously the green node extends to the right, or excuse me, to the left as well. But because that part of the circuit is just doing its own thing, I'm not really bothering with it right now. So essentially what I see is 10 ohms between the blue node and the orange node. And then I also see 7 ohms in series with 3 ohms, which is 10 ohms between the blue node and the orange node if I'm looking at the bottom path. So I know just by looking at this thing, essentially, that 1 amp of current is going to flow here, and 1 amp of current is going to flow down this way. Because according to current division, if I have two paths of equal resistance, the current should divide equally. So that means that 1 amp is going to wind up flowing into the negative polarity terminal of that 7 ohm resistor. And from that, VR at 0 plus is going to be negative 1 amp times 7 ohms is equal to negative 7 volts. Now, for what it's worth, I'll go ahead and show you what Colin was suggesting as well really quickly. So 2 amps in parallel with 10 ohms is going to wind up looking like 20 volts in series with 10 ohms. Then we would have our 3 ohm resistor, and then over here we would have our 7 ohm resistor, and then over here to the left is the rest of the circuit, which doesn't particularly matter to us. Here is the voltage drop that we are interested in, VR at 0 plus, and using voltage division, we would see that VR at 0 plus is going to be 20 volts times 7 ohms over 10 ohms plus 3 ohms plus 7 ohms. And the current that's flowing around this loop is flowing into the negative polarity terminal. So we should put a negative sign in front. And so that gives us negative 20 times 7 over 20 is once again negative 7 volts. So regardless of what way we choose to analyze the circuit, we're going to get negative 7 volts either way. So nothing remotely wrong with the way that you chose to look at it. I feel like my lazy current division way was easier though. Does anybody have any questions about this step before we, or any of the analysis performed before we move on to step number 3? All right. Let me just put a note here or that second analysis. All right. So for what it's worth, this particular step is only being included because of what we're going to do on Friday. Okay. So we're going to find here very quickly that for a circuit like this, where the sources are actually being taken out of our system, our analysis at t is equal to infinity, which is what step number 3 is always going to give us a result that is 0. Okay. So realistically, for what we're doing today, we could skip this step and not lose any information. But when we start working on systems where the sources are left in, then this step is going to matter. So step number 3 is to analyze the circuit at t is equal to infinity. And I'm just going to make another note here. This is also at DC steady state. Okay. So we're now looking at a system where our switch is closed at position B and our inductor looks like a short circuit. So if I draw that out, it would be something akin to this. So I think 2 ohm. Actually, I got those backwards. Sorry about that. Here is IL at infinity, and here is VR at infinity. And again, because our 5 amp source is essentially disconnected from our RL network on the right, we should see by inspection that IL at infinity is 0 amps and VR at infinity is 0 volts. Okay. So we could have completely and utterly skipped this step and it wouldn't have impacted anything. Simply because if we look back at our original equation, we're not asked for any information at t is equal to infinity. Okay. So this step will make way more sense on Friday. Step number 4 is going to be determine LEQ and REQ during the transient condition. I'm going to put an underline under during because that is incredibly important. Okay. So we have to avoid finding LEQ and REQ at t is equal to 0 minus, because that is before the transient condition happened. And so our switch hasn't yet changed states. And so some resistors might be switched in that shouldn't be, or some capacitors or inductors might be switched in that shouldn't count, etc. So generally speaking, I'm only going to give you circuits that are going to have, one resistance and then multiple energy storage elements that can be combined, or one energy storage element and multiple resistances that can be combined, so that we can generate a pretty straightforward methodology for determining the REQ and the LEQ or CEQ for our systems. So I want to scroll back up and look at our original circuit. So our original circuit only has a single inductor. So I'd love for you guys to take a crack at what you think LEQ is going to be. 100 millihenries. Thank you, Trevor. Absolutely correct. So since there's only one inductor in the whole damn system, LEQ has to be 100 millihenries. Literally can't be anything else. And I'm just going to make a note here, by inspection. So how we're going to find REQ is we're going to essentially determine the Thevenin equivalent resistance seen by our inductor, okay? So I'm just going to make a note here. REQ is the Thevenin resistance seen by the inductor. So because we're finding a Thevenin equivalent resistance, we need to be looking at a dead network during the transient condition, okay? So dead network, our current source is an open circuit because that's how we turn off a current source. Here is our 2 ohm resistor. This is our open circuited terminal A. Here's our switch closed at B. Ten ohm resistor, 3 ohm resistor. Up here are the terminals where my inductor was. So whenever I'm finding the equivalent resistance with respect to a particular element, I have to take that element out, and we're looking in through the terminals where our inductor was. So does anybody have any thoughts on what REQ might be here?
Is it 5?
It is indeed 5. It's just 10 in parallel with 10. So that's our REQ. So what I'm going to do now, and the reason for this should be pretty obvious here in a moment, is over here to the right, I'm just going to say that REQ divided by LEQ, so that's going to look like 5 ohms divided by our LEQ was 100 millihenries or 0.1 Henry, where a Henry is a volt second per ampere, also known as an ohm times a second. So our ohms are going to wind up canceling each other out. And we're going to have 5 over 0.1 is 50. And our units are going to be in per seconds. Okay. Okay. So before I move on to our last step, does anybody have any questions about how we determined LEQ and REQ for this system? All right. So our last step is simply going to be plug stuff in to our generic equation. I'm going to rewrite our generic equation down here for you guys. So our natural response, y sub n of t, is y at 0 minus for t less than 0 minus, and then y at 0 plus, e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. And we are interested in finding our inductor current and our resistor voltage. So let's start with our inductor current. What was the inductor current at t is equal to 0 minus? Scroll up and somebody tell me what it is.
2 amps.
2 amps. Thanks. Since the inductor current cannot change abruptly, it had to also be 2 amps at t is equal to 0 plus. So I've already got that part. E to the negative. What's Req over Leq?
50 per second.
So 50t amps for t greater than or equal to 0 plus. So there's my answer for IL of t. For VR of t, what was the voltage drop across our resistor at t is equal to 0 minus?
Zero.
So we have 0 volts for t is less than 0 minus. What was the voltage drop across our resistor at t is equal to 0 plus?
-7.
So -7 E Req over Leq is still 50, so -50 t volts for t greater than or equal to 0 plus. And we are done. So step number 5 is literally as easy as it sounds. We just plug stuff in and we're finished. Okay. All right. I have slightly less than 30 minutes left of class, so I'm going to go over how to handle RC circuits much more quickly. Okay. The same basic setup applies here, right? So let me just put a division thing here. So let's say that we have the following system where I have some voltage source, a switch which is opening at t is equal to 0, and then here I have some resistance Req, and here is some capacitance CEQ, like so. Actually, let me move Req to the other side just so that I can draw this a little better. CEQ over here as well. Okay. And so realistically, what we're most interested in here is the voltage drop across our capacitor, VC of t. And in this particular simplified example, our equivalent capacitance CEQ is in parallel with our equivalent resistance REQ. A couple of other quantities that we may be interested in would be our capacitor current, IC, as well as our resistor current, IR. Okay. So at t is less than or equal to 0 minus, our circuit would look something like this. Here's our source voltage. Our switch is closed. Here's REQ. Our capacitance is going to look like an open circuit because we're at DC steady state. Let's say that this is VC at 0 minus, IC at 0 minus, IR at 0 minus, and we can hopefully see very easily that VC at 0 minus is just going to be VS. And from this, the energy stored by our capacitance is going to be 1/2 CEQ times VS squared. Okay. At t greater than or equal to infinity. So once again, after our switch has changed states and we're back to a DC steady state condition, our circuit is going to look something like this. So here's VS, an open circuit representing our opened switch. Here's REQ. Our capacitor is once again going to look like an open circuit because we're at DC steady state. Here's VC at infinity. IC at infinity. IR at infinity. And we should be able to see by inspection that VC at infinity is 0 volts because the RC network is disconnected from the voltage source. And from this, our energy stored by our capacitor is 0 joules. So we have a similar situation. We have a capacitor that has some amount of stored energy. Our switch opens up. Capacitor dumps energy into the resistor, which converts it into heat. And if we wait long enough, all of the stored energy is converted into heat, and the capacitor voltage has to eventually fall back down to 0. So now let's figure out what's going on mathematically for 0 plus is less than t is less than infinity, which is our transient condition. So we have our voltage source is disconnected. Here's our equivalent resistance. Over here is our equivalent capacitance. By the way, if anybody has any questions, please interrupt me. I'd be happy to answer them. Here's IC as a function of time, IR as a function of time. And if we apply Kirchhoff's current law to this system, at the top right node, we'll wind up getting that IR plus IC have to be equal to 0. We can express both of those currents in terms of the capacitor voltage because it's common to both elements. So using Ohm's law, that's going to look like VC divided by REQ plus C times the derivative of VC with respect to time, which is once again a linear homogeneous first order differential equation. So if we guess that VC is of the form AE to the ST, like we did earlier with the inductor current, and we substitute that in, and we wind up rearranging, we wind up getting the relationship A times 1 over REQ plus S times CEQ, e to the ST is equal to 0, where this guy down here is once again our characteristic equation. And we have 1 over REQ plus S times CEQ is equal to 0, which means S has to be equal to negative 1 over REQ times CEQ. So what we'd find is that VC of t is equal to A e to the negative t divided by REQ times CEQ for 0 plus is less than t is less than infinity. And A is going to wind up looking like VC at 0 minus or VC at 0 plus, just for the exact same reasons that it was IL at 0 minus or IL at 0 plus for our inductor system. So that generically we can say that VC of t is VC at 0 minus for t less than, 0 minus, and VC at 0 plus e to the negative t divided by REQ, goodness, times CEQ for t greater than or equal to 0 plus. Goodness, I'm talking so fast, I'm running out of breath. And then if we wanted to go through the motions, we would wind up finding from Ohm's law that our resistor current will have this exact same form, and our our capacitor current is just the negative of our resistor current, so it will be of this same form, so that we could say generically y sub n as a function of time will be y of t for t less than 0 minus and y at 0 minus for t less than 0 minus y at 0 plus e to the negative t divided by REQ times CEQ for t greater than or equal to 0 plus. And so this is our generic equation for how we're going to look at RC circuits. And once again, we have 4 pieces of information that we're trying to find. Y at 0 minus, Y at 0 plus, REQ, and lastly, CEQ. So let's look at a quick example, and then we will wrap things up for today. So I'm going to try to make this one very easy so that we can go through it rather quickly. So here is our circuit of interest. So let's say that this voltage is 18 volts. Here we have some resistance in series with a switch that is opening at t is equal to 0. This resistor is going to be 20 kilo ohms. Now I'm going to have a capacitor here. So this first capacitor is going to be 6 microfarads. I'm going to have another resistor. Let's see, this will be 100 kilo ohms. I'm going to have yet another capacitor. This guy will be 12 microfarads. And for this particular problem, let's say that I'm interested in this voltage. Let's call it VC1. this voltage, which I'll call VC2, and this current, which I'm just going to call IR as a function of time. Okay. So our analysis procedure is going to be incredibly similar. Okay. The only thing that's really going to change is actually just going to be step 4, where we calculate CEQ instead of LEQ. Right. So step 1 remains analyze the circuit at t is equal to 0 minus. Okay. So at t is equal to 0 minus, our switch was closed. So our circuit should look something like this. So here's our 18-volt source. Here is a 20 kilo ohm resistor. Our switch is a short. Capacitor C1 is going to look like an open circuit. Here is our 100 kilo ohm resistor. Capacitor C2 is going to look like an open circuit. Here is VC1 at 0 minus. Here is VC2 at 0 minus. Here is IR at 0 minus. And I would love it if you guys would help me figure out what some of these quantities are.
They're all 0.
I disagree wholeheartedly. Only the current is 0.
Oh, the voltages are 18 volts.
Exactly right. So IR at 0 minus is 0 amps because there is no closed path that current can flow through anywhere in our system. And for that reason, the voltage drops across both of our resistors are 0, which means the voltage drops across both of our capacitors have to be 18 volts if we apply KVL around practically any loop in our system. So I'm just going to put here VC1 of 0 minus is equal to VC2 of 0 minus is 18 volts. Okay. Step number 2 is going to be to analyze the circuit. At t is equal to 0 plus. So at t is equal to 0 plus, our switch is now open. And we are during the transient condition, so our capacitors are no longer going to behave as open circuits. So we should have something that looks like this. So here is our 18-volt source. Here is the 20 kilo ohm resistor. Here's our switch as an open circuit. I'm not going to fill in what our capacitor is going to look like just yet. Not this capacitor either. So we should know that VC1 at 0 plus must be equal to VC1 at 0 minus. Sorry, let me make that one look less shitty. Because the voltage drop across a capacitor cannot change abruptly. So that means that this guy is 18 volts. And similarly, VC2 at 0 plus must be equal to VC2 at 0 minus, which would also be 18 volts. So the voltage drop across our capacitor is fixed. The current flowing through the capacitor is anything that it needs to be. So I'm going to choose to represent capacitors at t is equal to 0 plus with voltage sources. So here is a voltage source for VC1, or excuse me, capacitor 1. Here's a voltage source for capacitor 2. They need to have the same polarity as the capacitor voltages were defined, and they need to have the same value as what we found at 0 minus. So this is going to be an 18-volt source here and an 18-volt source here. And then the only unknown quantity is IR at 0 plus. Can anybody tell me what that is by inspection?
Maybe 36 volts over 100 kilo ohms.
I disagree.
It would be 0, no.
It'll be 0. So the voltage sources are in series, West, but they are of opposite polarities. So you would have negative 18 plus 100K times IR plus 18 is equal to 0, or 0 is equal to IR times 100K. All right, I'm going to skip step 3 because it's going to give us no information whatsoever, and we are so crunched on time, and move straight into step number 4. Okay. So step number 4 is going to be to determine REQ and CEQ during the transient condition. So to kind of help things along here, I'm going to turn off my 18-volt source. Here's the 20 kilo ohm resistor. And then over here to the right, I've got my capacitance C1, which was, I think, 6 microfarads. I've got my 100 kilo ohm resistor. And then I've got my second capacitor, which I believe was 12 microfarads. So this is my dead network, okay? So I have 2 resistors here, and I have 2 capacitors here. So we're going to have to think about this for a little bit. So I've drawn this during the transient condition with that switch open, which means that that 20 kilo ohm resistor is not part of any closed path whatsoever. So it shouldn't be influencing the value for REQ. So I believe very easily we could say that REQ in this case is 100 kilo ohms. Does anybody have any issue with that analysis? Okay, so since we know that REQ is 100 kilo ohms, our CEQ is going to be the Thevenin equivalent capacitance, essentially, seen by REQ. So if we take this 100 kilo ohm resistor out, leaving behind an open circuited set of terminals, what capacitance do we see?
It's 6 and 12 in parallel with each other, basically.
So I believe that they are in series with each other. The reason why I think that they're in series is if we look at our nodes, so we've got this node, and this node like so. So the purple and the blue are different nodes, which means they don't share both the top node and the bottom node. So they are not in parallel with each other. And because the 20 kilo ohm resistor isn't doing anything, I can effectively just throw that entire branch away, leaving what looks like a series connection. So for capacitors, 6 in series with 12 is going to look like 6 microfarads times 12 microfarads over 6 microfarads plus 12 microfarads, which, if my mental math is correct, is 72 over 18, which is 4. Somebody might want to check me on that one.
That's correct.
Okay. So now, just for the hell of it, I'm going to have 1 over REQ times CEQ is going to look like 1 over, so let's do 100 times 10 to the 3 ohms. Let's see, so that's 4 times 10 to the minus 6. A farad is an amp second per volt, or a second per ohm. So we can see that this ohm and this ohm cancels each other out. And I'm going to throw this into my calculator really quickly. 1 over, let's see, 100 times 10 to the 3 times 4 times 10 to the minus 6 winds up giving me 5 halves per second. So from here, I would go, actually, let me pause very briefly. Does anybody have any problems with how we determined REQ or CEQ for this network?
So CEQ for capacitance is parallel for resistors, basically.
So capacitors in series combine like resistors in parallel, and capacitors in parallel combine like resistors in series.
Understood.
Yep. So step number 5 is simply to plug stuff in to the generic equation. So I'm going to do that very quickly here. So VC1 of T is going to look like 18 volts for T less than or equal to 0 minus, and it's going to look like 18 e to the minus 5 halves T volts for T greater than or equal to 0 plus. Because the voltage drop across capacitor 2 was the same at both 0 minus and 0 plus, this is actually equal to VC2 as well. For IR, let's see here. What do we have going on at 0 minus 0 amps? And it was 0 plus 0 at 0 plus as well. So that's going to look like 0 amps for T less than or equal to 0 minus, and it'll be 0 e to the minus 5 halves T amps for T greater than or equal to 0 plus, which is literally just 0 amps for all T. Alrighty. I talked for the whole 110 minutes today. So for what it's worth, when we have our meeting on Friday, it will be much, much shorter, or at least I will talk way, way less. So yeah. If anybody has any questions, I would be more than happy to hang around over Zoom for another 3 or 4 minutes or so. But if not, I hope you have a great rest of your day, and I will see you on Friday.